Let us begin with chapter number 2. It is about rotational motion. First of all, let us introduce one specific body about which we are going to refer again and again in the entire chapter. That body is rigid body. Like any other body, rigid body is also a system of particles, but it is a specific system of particles in which relative positions of various constituent particles do not change with time. That is, they remain invariant with respect to time. In such a body, there is no change in length, no change in shape, no change in volume. I mean to say there is no deformation. Such a system of particles is called a rigid body. A system of particles in which relative positions of various constituent particles remain invariant with respect to time, do not change with time, is called a rigid body. A system of particles in which relative positions of various constituent particles remain invariant with time is called a rigid body. What is the difference between rigid body and a solid body? On every solid body, when you exert a force beyond a certain limit, at least there will be some slight deformation. So that is a solid body in which deformation is there. But according to definition, strictly if you have 100% rigid body, then in that there is no deformation at all. Let me tell you, 100% rigid body is our ideal imagination. In reality, it does not exist. Then you may have a question, when it does not exist in practice, why should we study that body here? Yes, your question is very important, but let me tell you, on a given solid body, up to certain limit of external force, if there is no deformation, then till that limit of external force, you can treat that solid body as a rigid body. No problem, correct? That's why. Now, let's go for understanding these two words, rotational motion and stationary axis of rotation. What do you mean by rotational motion? What do you mean by stationary axis of rotation? Let us see. Just to explain you in a better way, I have taken a spinning top. This is a top which is spinning about this vertical line, keeping itself at the same position. Fine. When it is spinning, what are the characteristics would you like to notice? First, you can see it's all constituent particles, they perform circular motions. Along with the spinning top, all the inside constituent particles, they perform circular motions. Not only that, second characteristic is that the centers of all these circular paths remain stationary over some definite straight line. Fine. Such a motion is called rotational motion, and that definite straight line is called an axis, stationary axis of rotation. Because it remains at rest, we call it stationary axis of rotation. Motion is called rotational motion, and that definite straight line is called axis of rotation for that rotational motion. Correct? How would you define it? Very simple. If all the constituent particles of a given rigid body perform circular motions, and if centers of their circular paths remain at rest, remain stationary over some definite straight line, then that motion is called rotational motion, and that definite straight line is called axis of rotation for that rotational motion. I repeat, if all the constituent particles of a given rigid body perform circular motions, and if centers of their circular paths remain stationary over some definite straight line, then that motion is called rotational motion, and that definite straight line is called axis of rotation for that rotational motion. Fine. If this axis does not change, then we call it stationary axis of rotation. In case of rotational motion of a rigid body about stationary axis of rotation, remember the planes of rotation, planes of circular motions of different constituent particles are found to be mutually parallel, but simultaneously perpendicular to stationary axis of rotation. You can see these planes x1 and x2, they are mutually parallel, but both of them are perpendicular to stationary axis of rotation. Okay. This r1 is the radius of circular path followed by this particle, r2 is the radius of circular path followed by this particle. Got it? Fine. Let's go for what is called rotational mechanics. There is a branch of physics in which we deal with the study of rotational motion of a rigid body. That very branch is known as rotational mechanics. Come on, that rotational mechanics has got two sub branches. One is called rotational kinematics, another is called rotational dynamics. Here and here, in both the branches, we definitely study rotational motion of a rigid body, but then there is a difference. What is the difference? I am showing you. When you study rotational motion of a rigid body in this branch, we do not make that study very much in detail. No, we do not specify the reasons responsible for rotational motion. We simply study rotational motion without mentioning those reasons. Such a superficial study is known as rotational kinematics. But when you make the study very much in detail by specifying the reasons responsible for producing rotational motion, not only that, you try to relate those reasons with the properties of a rigid body, then such a detailed study is known as rotational dynamics. In short, this is superficial study, this is detailed study. Okay, fine. Now, what is called angular position of a rigid body? This is bit a long definition, but you don't worry, I'll make all of you remembering the entire definition just now. Okay, you please try to understand first. What do you find in the figure? Tell me. Here is a rigid body having some irregular shape. Fine. You may show any other shape, no problem, but yet I would like to go according to textbook just to fetch maximum marks. Okay. In textbook you will find such a shape of a rigid body. Come on. Actually, this is a cross section of that body taken parallel to the plane of the figure. Fine. What does this body do? It performs rotational motion anti-clockwise this way about this stationary axis of rotation, say z axis, which is perpendicular to x, perpendicular to y. This one is z axis. About this axis, this body performs rotational motion this way. Okay, fine. Now, when it was performing rotational motion, we just had taken one photograph, and when we took that photograph, suppose it is found to be at this position. Okay. Now, just consider any one of the constituent particles for the purpose of study. That very particle is suppose this. Any particle, any constituent particle you may consider, whichever particle you are considering for the study of rotational motion, that very particle is known as representative particle. What is it called? Representative particle. Fine. It is called representative particle. It represents the entire rotational motion of a rigid body. Representative particle. Fine. Come on. At present for me, this is a representative particle which appears at position P at time t. You just do one thing, join this position with the center of its circular path. With the center of its circular path. That center is point O. In short, you just join O and P. Fine. So, which line segment would you get? Line segment OP. Fine. Now tell me, what is the angle made by this line segment with this x-axis, which at present we will take as reference line. Okay, fine. Now, when you join this point P with point O, you will get line segment OP. Find out angle made by this line segment with this reference line. It is this much angle. How much? Angle POX. Angle POX. Let it be theta. Fine. Tell me, what is that angle theta? It is angle POX. Angle POX. It is theta. That angle POX, which is theta, is only known as angular position. Is only known as angular position. But it is called angular position of a representative particle. And let me tell you, whatever is the angular position of representative particle, same is taken as angular position of entire rigid body at time t. Correct? Fine. How would you define it now? At a given instant of time, the angle made by a line segment joining position of any one of the constituent particles of a given rigid body with center of its circular path and a given reference line, that angle is called, come on, angular position of that representative particle and hence of that whole rigid body at that instant with respect to that reference line. Come on, repeat the definition. At a given instant of time, angle made by a line segment joining any one of the constituent particles of a given rigid body and center of its circular path with a given reference line is called angular position of that representative particle or of that particle and hence of that whole rigid body at that instant with respect to that reference line. I repeat, at a given instant of time, comma, the angle made by a line segment joining any one of the constituent particles of a given rigid body and center of its circular path with a given reference line is called angular position of that particle and hence of that whole rigid body at that instant with respect to that reference line. I repeat, come on. At a given instant of time, the angle made by a line segment joining any one of the constituent particles of a given rigid body and center of its circular path with a given reference line is called angular position of that particle and hence of that whole rigid body at that instant with respect to that reference line. Got it? Let it be now last time. Okay. At a given instant of time, comma, the angle made by a line segment joining any one of the constituent particles of a given rigid body and center of its circular path with a given reference line is called angular position of that particle and hence of that whole rigid body at that instant with respect to that reference line. Got it? My dears, no doubt this angle theta is angular position, but remember at time t. So this angle POX, which is theta, it is angular position of a rigid body at time t. Okay? But because this body is performing rotational motion this way, that is anti-clockwise, after some time it will get displaced this way. Correct? Come on. When it gets displaced this way, at time t plus delta t, the same representative particle which was earlier at point P, now it has been shifted to point P dash. Fine. Now tell me, if representative particle shifts its position, now new position is P dash, the way you are joining P with O, same way you have to join P dash with O. You have to join P dash with O. Fine. Come on, join it. Then which segment you will get? P dash O. Earlier, which was the angle? Angle POX. Now, the angle will be P dash OX. Come on, angle P dash OX. Suppose this much angle. How much? Angle P dash OP. I am just taking by symbol, say delta theta. Then tell me, what is this total angle? This total angle will be summation of this and this. Come on, theta plus delta theta. Say theta plus delta theta. So, new angular position at time t plus delta t is angle P dash OX, which is, come on, theta plus delta theta. Angle P dash OX is nothing but theta plus delta theta. Now tell me, let me find out change in angular position. Come on, change in angular position in time delta t. Tell me, particle is shifting from P to P dash in how much time interval? This minus this. So, Tt will cancel, giving you delta t. So, time interval taken by representative particle to shift from P to P dash is delta t. And when it does so, what is the change in its angular position? Let us find out. How do you find change? Change is always to be found out final minus initial. Final minus initial. Come on. Change in angular position would be final minus initial. What was final angular position? Theta plus delta theta. Initially it was theta. Final minus initial, theta theta will cancel, giving you delta theta. Fine. What is delta theta? Change in angular position. Same change in angular position is only known as angular displacement. Angular displacement. Change in linear position is called linear displacement. Change in angular position is called angular displacement, shown by symbol delta theta. And now we define what is called average angular speed. Wait. Whenever any body performs linear motion, it has some linear speed. Similarly, whenever any body performs rotational or angular motion, it must have angular speed. But that angular speed in practice is found in two different ways. Come on, first, when you find that angular speed in particular time interval, we call it average angular speed. If you find it at a particular instant of time, we call it instantaneous angular speed. Let us define both of them one by one. First of all, we go for average angular speed. It is to be shown by symbol average of omega. Come on, average of omega. Formula is very simple. Angular displacement divided by time taken. Angular displacement divided by time taken. Come on, when you want to define, you will take denominator 1 unit. So, define this now. Angular displacement undergone by a given rigid body per unit time is called its average angular speed. I repeat, come on, angular displacement undergone by a given rigid body per unit time is called its average angular speed. Is called its average angular speed. Once again, angular displacement undergone by a given rigid body per unit time is called its average angular speed, shown by symbol average of omega. Now, ultimately, what is it? Angle upon time. What is the SI unit of plane angle? Radian. What about SI unit of time? Second. So, unit of angular speed is radian per second. Now, let us see what is called instantaneous angular speed. It is to be shown by symbol omega. Now, tell me, this is instantaneous angular speed. Let me tell you, it is this average angular speed only. So, I should write delta theta upon delta t. Here it is delta theta upon delta t. But because we require instantaneous value, the time interval delta t is to be reduced, and it is to be reduced mathematically, you can say tending to 0, tending to 0. Value of delta t, we should make it smaller and smaller, smaller and smaller, smaller and smaller. There is no end to that. So, mathematically we write limit delta t tends to 0, limit delta t tends to 0. Now, in the language of calculus, this whole term can be written as, come on, d theta upon dt, d theta upon dt. When time interval is substantially small, differentially small, infinitesimally small, we just write dt, and in that extremely small time interval, very small angular displacement, we just show it by symbol d theta. Altogether, it is d theta by dt, or mathematically you may write d by dt of theta, d by dt of theta. Now, using this, you can define what is called instantaneous angular speed. Come on, define it from here. The time rate of change of angular position of a given rigid body is called its instantaneous angular speed. I repeat, the time rate of change of angular position of a given rigid body is called its instantaneous angular speed, shown by symbol omega. Mathematically, when you take derivative of angular position with respect to time, you will get, come on, angular speed. And normally, derivative with respect to time is shown by symbol of dot. So, you may write this whole symbol as theta dot, meaning thereby single time derivative of theta, because there is a single dot. Okay, fine. Now, this is the time interval, I mean scale of time. On this time scale, suppose this instant is t, this instant is t plus delta t, and now between these two instants, what is the time interval lapse? It is this minus this, so it is delta t. At time t, angular position is suppose theta. At time t plus delta t, angular position is suppose theta plus delta theta. Then what is the change in angular position? This minus this, it would be delta theta, which will give you angular displacement. Now, if you divide this delta theta by this delta t, then you will get it, come on, average angular speed in this much time interval. And in the same ratio, if you take limit delta t tends to 0, you are going to get instantaneous angular speed exactly at time t, exactly at time t. Got it? Fine. Now, we go for angular velocity. Angular velocity. Whenever angular speed is taken as a vector, we call it angular velocity. Angular velocity. It is to be shown by symbol vector omega. Fine. Now, you know, every vector has a specific direction. So, if angular velocity is a vector, then it also must have specific direction. To find out that specific direction, we use one law which is called right-handed screw. Law of right-handed screw. Law of right-handed screw is very simple. How to use that law? I am showing you. First of all, consider a rigid body performing rotational motion about stationary axis of rotation. At present, I have taken in the form of solid circular disc. Not necessary that you also should take the same shape. Not necessary. You may take any other shape, no problem. But here also, again I would like to go according to textbook. In textbook, they have taken such a shape. Okay. What does this solid circular disc do? It performs rotational motion about this stationary axis of rotation, which is passing through its center and perpendicular to its plane. Fine. Now tell me, this disc is performing rotational motion this way. Fine. To find out direction of its angular velocity, you know what we should do first? We should consider right-handed screw, and that screw should be considered in such a manner such that its geometrical axis should be parallel to the stationary axis of rotation of a given rigid body. You can see both these axes are parallel. And now, in the same manner as the body rotates, in the same manner you should rotate this right-handed screw also. If the head of that screw is at the bottom, you should just fix up that screwdriver like this, and then you should rotate it this way. Because the body is performing rotational motion this way. When you rotate it this way, come on, the whole screw will advance vertically upwards. If this screw advances vertically upwards, then according to law of right-handed screw, the direction of angular velocity of this rigid body should also be taken, come on, vertically upwards. That's why I am showing direction of vector omega vertically upwards. But not necessary that this disc should rotate like this only. Not necessary. It may rotate this way. If it rotates this way, don't bother. In that case, the screwdriver should be moved this way. Correct? And if you move the screw this way, the screw will move vertically downwards. At that time, direction of vector omega will be vertically downwards. Fine. In short, in case of rotational motion about stationary axis of rotation, direction of vector omega will be like this or like this. Come on, like this or like this means it is parallel to stationary axis of rotation. Got it? Fine. Now we go for average angular acceleration. Tell me, whenever there is a change in linear velocity, which acceleration is produced? Linear acceleration. Similarly, the bodies which perform rotational motion in practice, they may change their angular velocity. If they change their angular velocity, then because of that change, whatever acceleration is said to be produced in rotational motion is called angular acceleration, and it is shown by symbol vector alpha. But again, for angular acceleration also, if you find its value in a particular time interval, we will call average angular acceleration. If you find at a particular instant of time, we will call it instantaneous angular acceleration. Let us see one by one. First of all, we go for average angular acceleration, shown by symbol average of vector alpha. Fine. Now tell me, at time t, the instantaneous angular velocity of this rigid body is suppose vector omega, and it changes to vector omega plus vector delta omega at time t plus delta t. In short, in time interval delta t, the change in angular velocity that has taken place is this minus this, then it will be vector delta omega. You just divide that change in angular velocity by corresponding time interval, then you will get change in angular velocity per unit time, and that itself is known as average angular acceleration, shown by symbol average of vector alpha. Come on, define it. Change in angular velocity of a given rigid body per unit time is called its average angular acceleration. I repeat, change in angular velocity of a given rigid body per unit time is called its average angular acceleration, shown by symbol average of vector alpha. Now tell me about the unit. Unit of this would be unit of this upon this. Unit of angular velocity, come on, it was radian per second, upon unit of time is second. Bring this second down. So it is radian upon second square. Radian upon second square. Wait. Remembered? Linear displacement, linear velocity, linear acceleration. Which were the units? Meter, meter per second square. Similarly here, angular displacement, angular speed, angular acceleration. Come on, which are the units? Radian, radian per second square. Last time, linear displacement, linear velocity, linear acceleration. Here, come on, angular displacement, angular velocity, angular acceleration. What about the units? Here meter, meter per second square. Here radian, radian per second square. Simple? Fine. What about direction of angular acceleration? Direction of angular acceleration is in the direction of vector delta omega. But what do you mean by vector delta omega? Change in angular velocity. Now change in angular velocity in practice may take place in two different ways. Either angular velocity may increase with time or angular velocity may decrease with time. If angular velocity goes on increasing with time, consider direction of vector alpha in the same direction of vector omega. So at that time vector alpha will be also like this in the direction of vector omega if angular velocity keeps on increasing with time. Okay. But in case whenever angular velocity goes on decreasing with time, consider direction of vector alpha opposite to that of omega. Opposite to that of omega. Okay. In short, if angular velocity increases with time, vector omega and vector alpha have same directions, and if angular velocity decreases with time, then vector alpha and vector omega are in opposite directions. But in case of rotational motion of a rigid body about stationary axis of rotation, direction of vector alpha also will be either this way or this way, means very much parallel to stationary axis of rotation. Got it? Fine. What about instantaneous angular acceleration? It is to be shown by symbol only vector alpha. Only vector alpha. Let me tell you, it is this term only, vector delta omega upon delta t. But because you require instantaneous value, you should reduce this time interval. You should make it smaller and smaller, smaller and smaller, smaller and smaller. There is no end to that. So mathematically we write limit delta t tends to 0. Come on, limit delta t tends to 0. And now in this whole term, if you write that whole term in the language of calculus, you may write it this way, vector d omega upon dt, vector d omega upon dt. Now can you rewrite d by dt of vector omega, d by dt of vector omega. Using this, you can define now what is called instantaneous angular acceleration. Very simple. The time rate of change of angular velocity of a given rigid body is called its instantaneous angular acceleration. Is called its instantaneous angular acceleration. Repeat. The time rate of change of angular velocity of a given rigid body is called its instantaneous angular acceleration, shown by symbol vector alpha. Or mathematically, when we take derivative of angular velocity with respect to time, we will get, come on, instantaneous angular acceleration. Got it? Come on, now take the magnitude. Magnitude of this would be alpha. And here when you take magnitude, it would be d omega upon dt, d omega upon dt. Come on, rewrite d by dt of omega, d by dt of omega. But what is omega? What is omega? Omega itself is d theta by dt. Omega itself is d theta by dt. So what is this? Derivative of theta taken once with respect to time. This is taken second time. Altogether 2 times. We write it this way, d 2 theta upon dt square. See how is the pronunciation. Don't speak haphazardly. Speak out this way. d 2 theta upon dt square. Here 2 and here square. d 2 theta upon dt square. It is going to give you double derivative of theta with respect to time. I told you single derivative then single dot. Single derivative then single dot. Here double derivative, then it is double dot. Okay. So alpha equals to theta double dot. Got it? Fine. Come on, my dears. Let us proceed further in chapter number 2. Today we are going to discuss very important theories. Please try to understand them. Look in the figure now carefully. Look. First article today will discuss about relationships between linear velocity and angular velocity. We will obtain 2 types of relations. One is scalar relation, another is vector relation. Okay. In the textbook, you may not understand the derivation of vector relation. Here you will understand it perfectly. Just look in the figure now. Last time, if you have remembered, we had considered one rigid body which was rotating about this z axis, correct, which was perpendicular to x and y axis, and that rigid body was rotating this way, correct. When you view from front side, it was rotating anti-clockwise this way, fine. And for the study of that rotational motion, we had considered one particle, and last time we had given name to that particle. Remembered? Representative particle. And that representative particle was found to be at point P at time t. Correct? Fine. Later on in delta t time, the same particle had gone to new position, which was P dash. Remembered? And then while going from P to P dash, it undergoes this much angular displacement, and that angular displacement last time we had shown by symbol delta theta. Remembered? And this particle was performing circular motion on a circle of radius this much. OP or OP dash, both of them are same, and that same radius we have taken by symbol small r. Okay. Don't you know how measurement of plane angle is defined in radian? Do you know the formula? Angle equals to arc upon radius. Angle equals to arc upon radius. Angle is this much, delta theta. Arc is this much from P to P dash, divided by radius is r. Correct? Fine. Now let me find out average linear speed of this representative particle when it goes from P to P dash. Come on, average linear speed is nothing but path length upon time taken. Path length upon time taken. What is path length from P to P dash? It is arc PP dash. Arc PP dash divided by time taken for that. It is delta t. Correct? Now this average of V as it is. What about arc PP dash from here? Find out from here, transfer this. PP dash would be r into delta theta. PP dash equals to r into delta theta. Correct? Upon delta t. Fine. Now this is average speed of representative particle in time interval delta t. Suppose I want instantaneous speed of representative particle at time t at position P. For finding instantaneous speed, what you are supposed to do? You are supposed to reduce time interval smaller and smaller, smaller and smaller. Mathematically we can write limit delta t tends to 0. Limit delta t tends to 0. So in this ratio, if you reduce this time interval gradually tending to 0, then mathematically you may write limit delta t tends to 0. Same ratio I have written here, r delta theta upon delta t. And when you do that, you will get instantaneous linear speed of representative particle at time t. Let it be shown by symbol only small v. Now tell me, this radius is constant. It has got nothing to do with the time, whether you consider less time or you consider more time. For this particle, the radius of circular path will remain same. So because r is constant, I can take it out. When I take it out, the remaining part is limit delta t tends to 0, delta theta upon delta t. Limit delta t tends to 0, delta theta upon delta t. Now tell me, r as it is, correct? But in the language of calculus, what is this? What is this in the language of calculus? It is d theta by dt. And tell me, last time we had studied time rate of change of angular position gives you instantaneous angular speed shown by symbol omega. R as it is, this d theta by dt is nothing but omega. Got it? So ultimately what have we got? V equals to r omega. V equals to r omega. This is nothing but scalar relation between vector v and vector omega. Scalar relation means relation between only magnitudes, and that is right now v equals to r omega. Got it? Now let us obtain vector relation. Now try to understand this figure very nicely. In the textbook, in the first figure, they had considered plane of rotation of representative particle which is the plane of the figure, which is surface of board, which is vertical plane, correct? But in this figure, you know what have they done? They have changed the plane of rotation. Instead of vertical plane, now they have chosen horizontal plane, correct? They have considered this representative particle as if it is rotating this way, correct? And when it is revolving this way, the plane of revolution would be horizontal plane. And that horizontal circular path I have shown here. Horizontal circular path I have shown here. And suppose at time t, the representative particle comes at this very position, say point P. When it comes here, what is its position vector with respect to center of its circular path? That center is O, that position vector is vector OP, which in the figure I have shown by symbol vector small r. Fine. Now extend this vector in the same direction with the same magnitude. So same vector I have shown here in the same direction. I have simply arranged that vector ahead. Okay. So these two vectors having same directions, same magnitudes must be equal. If this is vector r, these also must be vector r. Fine. Now tell me, at any point, what is the direction of instantaneous velocity? You know from first semester, direction of instantaneous velocity is always along the tangent drawn to the path of motion at a given point. So at this very point, on this path, if you draw a tangent, it will be like this, and in this direction, there is instantaneous linear velocity of representative particle at time t. Fine. So this is vector v, okay? This is vector r. Wait. This rigid body is assumed to be rotating this way. If it is rotating this way, come on, what is the direction of angular velocity? Last time we had found out using law of right-handed screw. Come on, when the body is rotating this way, direction of, come on, angular velocity was found vertically upwards. That's why vector omega I have shown vertically upwards, correct? And same vector, you just shift it, bring it here. Same vector I have shifted here, so this is now vector omega. And suppose this body has, come on, angular velocity which is increasing with time. If angular velocity goes on increasing with time, then direction of angular acceleration is same as direction of angular velocity. So in that case, vector alpha and vector omega will point in the same direction, And that's why I have shown vector alpha in the same direction. Come on, this vector alpha I have shifted, I have brought over here, correct? So this is now vector alpha. Fine. Now suppose I want to find out direction of such a vector product. Which vector product? Vector omega cross vector r. Which vector product I want? Vector omega cross vector r. How to find vector omega? This way. How to find vector r? This way. Now situation is like this. Look, take this as vector omega, correct? Take this as vector r. So this is vector omega, this is vector r. Come on, they are at right angles. This angle is 90 degree. This is vector omega, which I am holding here this way, and this vector r I am holding here. This is vector r. Now tell me, how to find their tails? Their tails are superposing at the same point. Tail of this vector is here, tail of this vector is at the same point. And now we want direction of vector omega cross vector r. Think of a plane passing through these two vectors, and then after think of a right-handed screw which is perpendicular to this plane, correct, this way. And now I am supposed to rotate this screw in a manner first vector rotates towards second vector. First vector is vector omega, second is vector r. Rotate vector omega towards vector r this way. When you rotate this way, come on, the same way you should rotate this right-handed screw. When I rotate this right-handed screw in this manner, look, this way, correct? It will advance in this direction, correct? it will move forward in this direction. And you know, according to law of right-handed screw, the direction of advancement of right-handed screw should be taken as direction of vector product. So direction of this vector product is in this direction. In this direction means in the direction of linear velocity. In the direction of linear velocity, that is vector v. This vector product is found to be in this direction. Got it? Now let me find out magnitude of such a vector product. Let me find out modulus of vector omega cross vector r. Don't you know from first semester, modulus of vector A cross vector B, how much it is? A B sin theta. A B sin theta. Similarly here omega r sin theta. Omega r sin theta. What is theta? Angle between vector omega and vector r. Angle between vector omega and vector r. How much is that angle? It is 90 degree. Fine. So that angle which is 90 degree, come on, sin 90 is 1 into omega r will give you omega r. But what is omega into r? What is omega into r? It is nothing but v. Omega into r is nothing but v. Just right here. Omega into r is nothing but v. But what is v? It is modulus of vector v. So these two are such vectors whose directions are also same, whose magnitudes are also same. Two vectors having same magnitude, same direction, having same magnitude, same direction. They are none but equal vectors. So you can write this vector equal to this vector, that is vector v equals to vector omega cross vector r. This gives you vector relationship between linear velocity and angular velocity. Mind well, scalar product is commutative. So there you can change the order. You may write here v equal to r omega, or you may write v equal to omega into r, no problem. But vector product is not commutative. You cannot change the order. You cannot change the order. In the same order you must write. And at all, if you want to change the order, you can change it by putting negative sign. Because in semester 1 you had studied vector A cross vector B is equal to minus of vector B cross vector A. So you may write this way, or if you want to write with the reverse order, you may write minus sign outside, inside the bracket vector r cross vector omega. Okay, fine. This is the vector relationship between linear velocity and angular velocity. And now let us obtain relationship between accelerations. One is linear acceleration, another is angular acceleration. Come on, relations between linear acceleration, that is vector A, and angular acceleration, that is vector alpha. See, this derivation depends on this final result which we have obtained just now. If you don't remember this result, you cannot proceed further in this theory. So please, in any case, you must not forget this relation. Okay, remember it anyhow. Vector v equals to vector omega cross vector r. Now just take derivative with respect to time on both the sides. Derivative with respect to time on both the sides. D by dt of vector v equals to d by dt of vector omega cross vector r. What is left hand side? Tell me. Vector dv by dt. Vector dv by dt. Fine. But on right hand side, what are you doing? You are taking derivative of a cross product. Time derivative of a cross product. There is a special rule in mathematics. I am showing you that rule 2 to 3 times. You must remember now. Come on. Rule is that derivative of first vector, derivative of a vector product. Derivative of a vector product. You must take it this way. First vector as it is, cross product with derivative of second vector plus derivative of first vector cross product with second vector. Never say into, say cross product. Say cross, don't say into. Take care while pronouncing, okay? I repeat, first vector as it is, cross product with derivative of second vector plus derivative of first vector cross product with second vector. Last time, vector omega cross vector dr by dt plus vector d omega by dt cross vector r. See, if somebody wants to write in place of this term, somebody wants to write this term, and in place of this term, somebody wants to write this term, no problem. You can interchange the positions of these two terms because vector addition is commutative. Vector addition is commutative. But in a given term in which you find vector product, in that term you cannot change the order because vector multiplication is not commutative. Vector product is not commutative. Because vector product is not commutative, you cannot change the order. Okay? In effect, if at all you want to change the order, you can change the order by putting a negative sign. Now tell me last time, vector omega as it is, cross product with derivative of second vector, that is vector dr by dt, plus derivative of first vector, that is vector d omega by dt, cross product with second vector, that is vector r. Now just tell me identification of each quantity. Time derivative of velocity, come on, derivative of velocity with respect to time or time rate of change of velocity will give you acceleration. Because this is linear velocity, this will give you linear acceleration, vector a, small a. Vector omega as it is, cross product as it is, time rate of change of position vector, time rate of change of position vector will give you linear velocity, vector v, plus time rate of change of angular velocity. Last time we had studied, it is nothing but angular acceleration, vector alpha, cross vector r. Got it? I repeat, time rate of change of linear velocity will give you linear acceleration, vector omega as it is, time rate of change of position vector will give you instantaneous linear velocity, let it be vector v. Come on, time rate of change of angular velocity will give you angular acceleration, vector r as it is. Got it? Now this equation gives you vector relationship between linear acceleration and angular acceleration. Okay? This gives you vector relation between these two accelerations. Now let us obtain scalar relation. Tell me, if vector is this plus this, I say both of these terms, this and this, both of them, I say they indicate some sort of acceleration. Why? Because addition of two accelerations only can give you acceleration. Addition of two accelerations only can give you acceleration. You can make addition and subtraction of homogeneous quantities. Homogeneous means identical type. If this is acceleration, these also must be acceleration, these also must be acceleration. Okay? Let us find out their directions. And from directions, we will give them some specific name. First of all, come on, take out this one, take this one, vector omega cross vector v. Look, vector omega cross vector v, fine. Now, in which direction this vector product lies? Let us find out. You want vector product, come on, vector omega cross vector v. This is vector omega. This is vector v. Now, situation is like this. Look, this is vector omega, say this is vector v, situation is like this, vector omega is shown here, this vector v is this, correct? And now, the angle between them is right angle, this angle is 90 degree, correct? Fine. Now, think of a plane passing through these two vectors, correct? Now, think of a right-handed screw which is perpendicular to that plane, this way. And now I am supposed to rotate this screw in a manner, first vector rotates towards second vector. First vector is vector omega, second vector is vector v. I am supposed to rotate omega towards v, this way, correct? And in the same manner, I am supposed to rotate this screw. If I rotate this screw this way, correct? It will advance in this direction, from P to O in this direction, from P to O. From P to O. But what is point O? It is the center. So any direction which is pointing towards the center is called centripetal. Centripetal. That's why name of this acceleration, first name is given, come on, centripetal acceleration. Moreover, it is on this radius from P to O. What is it? Radius of this circular path. Because its direction lies along the radius, we call it by another name, radial acceleration. So either call it, come on, centripetal acceleration or radial acceleration. Because it is acceleration, we write A. Because it is radial acceleration, we write suffix as R. And you know, vector product will always give you vector. That's why symbol of this term is vector AR. Symbol of this term is vector AR. Got it? Fine. Now, let us obtain the formula for radial acceleration. I am showing you how to get it. Take magnitude on both the sides. Correct? When you take magnitude, come on, take magnitude here also. Magnitude of vector AR is simply AR. Magnitude of vector A cross vector B, what is it? AB sin theta. Similarly here, omega V sin theta. Theta is right now 90 degree. Angle between vector omega and vector V, you can see it is 90 degree. Correct? Fine. Now sin 90 is 1. So giving you one formula which is omega into V. But don't you know, V equals to R omega. V equals to R omega. Come on, put V equal to R omega. V equals to R omega. Correct? Omega into omega, that is omega square into R. And now, just find out omega from here. Find out omega from here, it will be V upon R. Omega equals to V upon R. Omega equals to V upon R. V upon R into V. V upon R into V. How much it is? V square upon R. Say V square upon R. So there are three formula for AR. Come on, first is omega into V. Second is omega square R. Third is V square upon R. Omega into V, omega square R, V square upon R. Omega into V, omega square R, V square upon R. Fine. And tell me, how to find this direction? This direction is along radius, and for a circular path, radius and tangent are always mutually perpendicular. So along tangent, there lies the path of the particle. So this is the path and this is the perpendicular to that path. So in short, direction of this acceleration is perpendicular to path of motion. Because it is perpendicular to path of motion, in the semester number 1, you had shown by symbol A perpendicular. Come on, A perpendicular, correct? So you can just show it by symbol AR also, or you may show by this symbol A perpendicular. Remembered from semester 1, what was the effect of this perpendicular component of acceleration? Under the effect of A perpendicular, come on, its effect is to just change the direction of velocity. Just to change the direction of velocity. Radial or centripetal acceleration simply changes direction of velocity. It does not change the magnitude of velocity. Got it? And now tell me. Take another part now. Second term is this. Second term is this. Which one? Vector alpha cross vector R. Come on, concentrate here now. Vector alpha cross vector R. Let us first of all find out its direction, and depending upon that we will be giving name to it. Come on, vector alpha cross vector R. I want vector alpha is this, correct? Vector R is this. Now situation is like this. This is vector alpha, correct? This is vector R. Vector alpha, vector R, angle between them is 90 degree. Come on. Situation is like this. Now think of a plane passing through these two vectors. And now you should consider right-handed screw perpendicular to that plane. Let it be this screw. Come on, this way. And now I am supposed to rotate this screw in a manner. First vector rotates towards second vector. First is vector alpha, second is vector R. I am supposed to rotate vector alpha towards vector R. Vector alpha is rotated towards vector R. This way. Now tell me, if you rotate this screw in this manner, correct? This way. Then it advance this way. That is in the direction of velocity. In the direction of velocity means what? In the direction of tangent, because this velocity is always along tangent. Because direction of this is along the tangent, we call it, come on, tangential acceleration. What do we call it? Tangential acceleration. And for tangential we write T, for acceleration we write A, and you know vector product will give you always vector. That's why the symbol is vector AT, tangential acceleration. Tangential acceleration. Got it? Fine. Take modulus on both the sides. Mod of this is mod of vector AT, and here mod of vector alpha cross vector R. Come on, modulus of this, it is 80. Vector A cross vector B, what is its magnitude? A B sin theta, A B sin theta. Similarly here, alpha R sin theta. What is theta? Angle between vector alpha and vector R. Angle between vector alpha and vector R, you can see it is 90 degree. Correct? Fine. Now tell me sin 90 is 1. So giving you only one formula, alpha into R. For tangential acceleration, there is only one formula. Please remember, it is alpha into R. And in semester 1, you are calling this acceleration as a parallel, because its direction is along tangent. Along tangent means parallel to short path which is considered at point P. If its direction is parallel to this path, then we call it parallel component. That's why in semester 1 you had shown by this symbol a parallel. And what was its effect? Its effect was to change the magnitude of velocity. Remember, radial or centripetal acceleration simply changes direction of velocity, and tangential acceleration always changes only magnitude of velocity. Got it? Fine. Now tell me, this representative particle performs circular motion. That circular path I have shown here. Okay? And that representative particle comes at point P at time t, and at that time if somebody is asking you what is the direction of radial acceleration or centripetal acceleration, it is always pointing towards the center, and that vector I have shown by symbol vector AR, that is radial or centripetal acceleration which is pointing towards the center. Somebody is asking you where is the tangential acceleration, then you must show tangent. Come on. This is the direction which gives you tangent drawn to this circular path at this very point, which is perpendicular to this radius, this way, correct? Now this vector 80, I am just shifting from here to here, correct? And when you shift it from here to here, come on, vector AR plus vector 80, look here, vector AR plus vector 80 will give you total acceleration. So this vector plus this vector will give you this vector, that is vector A. And now tell me, don't you find it on the hypotenuse? Come on, opposite to right angle, it is hypotenuse. According to Pythagoras theorem, square of hypotenuse will be, come on, summation of squares of these two, or you find out measurement of this hypotenuse, it is A equals to, come on, square root of summation of squares of mutually perpendicular sides. So A will be equal to under root of AR square plus AT square. A equals to under root of AR square plus AT square. Find out AR square from here. AR square will be how much? Omega square V square. Come on, omega square V square plus AT square. Come on, AT square will be alpha square R square. AT square will be alpha square R square. Now tell me, what does this give to you? It gives scalar relationship between linear acceleration and angular acceleration, because it is the relation between only magnitudes. This is scalar relation and this one is vector relation. Okay, fine. Now tell me, V square, you just find out from here. What is V square? V square will be, come on, R square omega square. V square equals to R square omega square. Come on, V square equals to R square omega square. Omega square into omega square, omega raised to 4, and plus alpha square R square as it is. Alpha square R square as it is. Take R square common, and when you take common, and if you want to bring it out, after taking square root only you can bring it out. What is square root of R square? It is R into under root of omega raised to 4 plus alpha raised to 2. Under root of omega raised to 4 plus alpha raised to 2. And now tell me, R as it is, come on, under root of, what was omega? Instantaneous angular speed. It is nothing but time rate of change of angular position. Last time we had defined omega equals to d theta by dt whole raised to 4, don't forget. And we had proved last time alpha, angular acceleration is nothing but double derivative of angular position with respect to time, that is d 2 theta upon dt square. d 2 theta upon dt square, second order time derivative of angular position gives you angular acceleration, and don't forget to make it squared, correct? So this is also another equivalent formula for magnitude of total linear acceleration. Got it? Fine. Come on my dears, now read the statement of illustration number 1. Illustration number 1. Just read the statement. Come on, have you read it? Look. We are given a second arm or second hand which is rotating on some dial of some clock. Length of that second hand they have given 20 centimeter. The dial is this and that second hand is this. Now tell me, for this second hand its length is this much, which will also give you radius of circular path followed by the particle at the tip of that second hand. Okay, that radius is equal to length of second hand, which is 20 centimeter. First of all, we are asked to find out its constant angular speed. Fine. Whatever the arm may be second arm, minute arm, hour arm, for whichever arm or whichever hand, you know its respective angular speed is going to remain constant with time. So don't write here average omega, you may write only omega because omega is constant. Now what is angular speed? It is after all angular displacement upon time taken, angular displacement upon time taken. Now my dears, I am just showing you very good way to remember this formula and to apply that formula. See what the students do, they simply mug up the formula, but they don't know how to apply that formula. See here, you may take any time, no problem, but the condition is that in the numerator you must write that angular displacement which is undergone in this time. Okay, or you may speak reverse. Here you may write any value of angular displacement, but the condition is that in the denominator you must write corresponding time in which this much angular displacement is undergone. Got it? Fine. So respective values you must put. Let me allow this second hand to finish one rotation, and as it finishes one rotation means what? 360 degree angular displacement. But 360 degree means 2 pi radian. Come on, 2 pi radian. So this delta theta at present I am taking 2 pi radian. Fine. Then corresponding time I must write in the denominator. Let me write it. You know second hand finishes one rotation exactly in 1 minute. But 1 minute means what? 60 seconds. That's why I am putting here time in second. Come on, 60 second. Okay. So it is 2 pi radian upon 60 second. Suppose somebody wants to allow that second hand to finish 2 rotations, suppose, no problem. In one rotation, this much is the angular displacement, 2 pi radian. Then in 2 rotations, it will be 2 into 2 pi, 2 into 2 pi. But then in the denominator, you are supposed to write corresponding time, which is time for 2 rotations. What is time for 2 rotations for second hand? It is 2 minutes. 2 minutes means 2 into 60 seconds, correct? So here also you get multiplied by 2, here also you get multiplied by 2, 2 will cancel. And now tell me, take this 2 in the denominator, 60 upon 2 will be 30. So it is now pi upon 30, that much is the constant angular speed of every second hand in any clock, okay? Fine. Come on, unit of angular speed is radian per second, okay? And now we are asked to find out linear speed for that particle which is situated at the outward end of this second hand. For this outer end, for this particle, you can see it is revolving on a circular path having radius small r. Then just now you have obtained scalar relationship between linear velocity and angular velocity. What was that? V equals to r omega. V equals to r omega. Come on, V equals to R omega. Now this radius is, come on, 20 centimeter. If you take this radius in centimeter, naturally this will be obtained in centimeter per second. Radius is 20 centimeter. What about constant angular speed? Just now we have found out it is pi upon 30. Pi upon 30. Now 1 0 is getting cancelled. 2 pi by 3. That many centimeter per second. What about angular acceleration? For any arm, might be second arm, minute arm, hour arm, because each arm moves with a constant angular speed. There is no angular acceleration. No angular acceleration, then mathematically alpha is 0. Alpha is 0. Correct? What about radial acceleration? Radial acceleration formula just now we had obtained. AR equals to, come on, V square upon R. AR equals to V square upon R. Come on, V square. Square of this means square of this. Take square of this, come on, 4 pi square upon 9. 4 pi square upon 9 upon R. R is how much? 20 centimeter. Now 4 5s are 20 and this 9 will come down. 9 5s are 45. Pi square as it is. This much is the acceleration in centimeter per second square. Okay. Now they have put a note in the textbook that repeat all these values, calculate them again for a minute arm of length 15 centimeter and for hour arm of length 10 centimeter. Fine. I am showing you how to calculate angular speed for these arms. Rest of the values are very easy to find out. Look, same formula of omega I am using now, delta theta upon delta t. Omega equals to delta theta upon delta t. Suppose minute arm is also allowed to rotate once. When minute arm finishes one rotation, its angular displacement will be also 2 pi radian. In one rotation, angular displacement is always 2 pi radian, but divided by corresponding time taken. You know, when minute arm finishes one rotation, then time taken is 1 hour. 1 hour is 3600 seconds. Simple. Now tell me, if you divide by 2 here, then it is pi upon 1800. Pi upon 1800 radian per second. Fine. This much is the constant angular speed of every minute arm in every clock. Okay. Then we go for hour hand. For hour hand or hour arm, tell me, apply the same formula. Omega equals to delta theta upon delta t. Omega equals to delta theta upon delta t. What is delta theta? Let our arm also finish one rotation. In one rotation, what is angular displacement? 2 pi radian. So delta theta I am putting 2 pi radian. But divided by corresponding time taken. See, now if it is our arm, when our arm finishes one rotation, then it will be taking 12 hours to do that. Because here if you assume 12 o'clock, then here it is 3 o'clock, here it is 6 o'clock, here it is 9 o'clock, here again 12. So if it starts at 12 noon, then it will finish one rotation and at that time it will be 12 midnight. Okay. So from 12 noon to 12 midnight, it is 12 hours. And for 12 hours, what is the time in second? 1 hour is 3600 seconds. So 12 hours will be 12 into 3600, that many seconds. Okay. So in short, in all the three hands, have you seen numerator remains same, 2 pi radian, come on, 2 pi radian, come on, 2 pi radian. But here denominator is 60 second, here denominator is 3600 second, and here it is 12 into 3600 second. Got it? Fine. Now just divide by 2 here. 12 into 3600 divided by 2, that gives you answer 21,600. Pi as it is. Okay. Pi upon 21,600, that many radian per second. Okay. Fine. Now next theory is very important. Remember in semester 1, you had obtained 3 equations of linear motion performed with constant linear acceleration. Remember those 3 equations? Let me remind you. V equals to V0 plus AT. D equals to V0t plus 1 by 2 AT square. V square minus V0 square equals to 2AD. Remembered? Come on. Similar 3 equations today we will obtain for rotational motion. How? I am showing you. Look, Consider this as time scale on which this beginning first moment I am taking t equal to 0 and this later moment I am taking t equal to t. At t equal to 0, initial angular position of a given rigid body is suppose 0. At time t, final angular position I am taking as theta. So, what is change in angular position? It is delta theta, it is theta minus 0. Theta minus 0, that is theta. Fine. And here, what is the time interval lapse? Time interval lapse is t minus 0. T minus 0, that is t. What is the change in angular speed? Wait. At time t equal to 0, initial angular speed of a rigid body performing rotational motion with constant angular acceleration about stationary axis of rotation, I just assume omega 0, initial angular speed. At time t, final angular speed I assume omega. So, what is change in angular speed? Delta omega would be final minus initial, omega minus omega 0. Fine. Now, tell me, what is average angular acceleration? Last time we had defined average of vector alpha. It was change in angular velocity divided by time taken. Now, just take magnitude on both the sides. So, when you take magnitude, instead of this vector sign, you just delete vector sign, average of alpha, delete this vector sign, delta omega upon delta t. Now, no need to write average alpha because alpha value is right now constant. If angular acceleration is constant, instead of average alpha, we may write simply alpha. See, when we will need average if the quantity is changing with time. But if quantity is remaining constant, you should not find average. And even if you find average, you will be getting same as constant value. So, instead of average alpha, I am just putting alpha. And here change in angular speed, delta omega is how much? Omega minus omega 0. Omega minus omega 0. Upon corresponding time interval, delta t is simply t. Okay? Transfer this. When you transfer, it is now omega minus omega 0 equals to alpha into t. And transfer this minus omega 0 on this side will become plus. Omega equals to omega 0 plus alpha t. Omega equals to omega 0 plus alpha t. This is the first equation of rotational motion of a rigid body performing about stationary axis of rotation with constant angular acceleration. Okay? And don't you find that equation quite similar, quite analogous to first equation of linear motion performed with constant linear acceleration? Recall that equation, v equals to v0 plus at. Come on, here final linear speed, here final angular speed, here initial linear speed, here initial angular speed, here constant linear acceleration, here constant angular acceleration. Got it? Fine. Let us start with this equation now. Last time we had defined average angular speed. It was nothing but angular displacement upon time taken. Now, here angular acceleration is constant. So, angular speed will change with constant rate. And then tell me, if you need to find out average, whenever alpha is constant, you need to find out average of omega. Simply, you can add initial and final angular speeds and then you can divide by 2. Summation of 2 angular speeds divided by 2. Summation of 2 angular speeds divided by 2. That will give you average. So, what is this average value? Omega plus omega 0 upon 2. Summation of 2 angular speeds divided by 2. And this delta theta is how much? It is theta. Delta t is t. Delta theta is theta. Delta t is t. And now transfer this t over here. Theta will be omega plus omega 0 by 2 into t. This equation is also similar to this equation which we studied in semester 1. D equals to V plus V0 upon 2 into t. Instead of linear displacement, you find angular displacement. Instead of initial linear speed, you find initial angular speed. Instead of final linear speed, you find final angular speed. Simple. And now, just put the value of, come on, omega. Put the value of omega. Omega equals to omega 0 plus alpha d. Omega equals to omega 0 plus alpha d. Put it here. Put it here, omega equals to omega 0 plus alpha t plus omega 0 upon 2 into t. Now tell me omega 0 plus omega 0, how much it is? 2 omega 0. And then alpha t as it is divided by 2 as it is, t also as it is. Now just divide by 2. 2 omega 0 upon 2. How much it is? Omega 0. Alpha t upon 2, that is 1 by 2 alpha t. 1 by 2 alpha t. Take this t inside. Just multiply omega 0 into t plus 1 by 2 alpha t into t, that is t square. Correct? Theta equals to omega 0 t plus 1 by 2 alpha t square. This equation is quite similar to second equation of linear motion performed with constant linear acceleration. Remembered? D equals to V0 t plus 1 by 2 AT square. Come on, check the similarity or analogy. Come on, this is linear displacement, this is angular displacement. Initial linear speed, initial angular speed. Come on, constant linear acceleration, constant angular acceleration. Got it? And now just find out value of t from equation 1. What is value of t? Come on, omega minus omega 0 upon alpha. T equals to omega minus omega 0 upon alpha. T equals to omega minus omega 0 upon alpha. Put this value of t from equation 4 into equation 2 over here. Start with this. Theta equals to omega plus omega 0 by 2 as it is into t is how much? Omega minus omega 0 upon alpha. Omega minus omega 0 upon alpha. Come on, multiply. If it is a plus b into a minus b, what is it? A square minus b square. Similarly here, omega square minus omega 0 square, and here it is 2 alpha. Correct? Now transfer this. When you transfer, omega square minus omega 0 square equals to 2 alpha theta. 2 alpha theta. Come on, give it equation number 5. Fine. Now this equation is quite similar to this third equation of linear motion performed with constant linear acceleration. Remembered from semester 1, v square minus v0 square equals to 2ad. Final linear speed, final angular speed. Initial linear speed, initial angular speed. Constant linear acceleration, constant angular acceleration. Linear displacement here, angular displacement. Okay. Now, which are called linear variables. Variable means that quantity which can change, okay, which can change, which can differ is known as variable. Fine. Linear variables are 3: linear displacement, linear velocity, linear acceleration. Similarly, there are 3 angular variables or 3 rotational variables. Come on, angular displacement, angular velocity, angular acceleration. Now, to make the study of rotational motion of a rigid body, you may use linear variables, you may use rotational variables, no problem. But in practice, we don't use these linear variables, no, we don't use them, we prefer to use these angular variables. You know what is the reason? See, whenever rigid body is performing rotational motion about a stationary axis of rotation with constant angular acceleration, remember, we find that all these angular variables are same for all the constituent particles. If all the angular variables are same for all the constituent particles, then we need not to study the rotation motion of each and every particle. We don't do that. We simply concentrate only on one particle, which is called representative particle, and whatever is the study of rotation motion of that representative particle, same study is applicable for all other constituent particles. That's why our study of rotational motion would become very easy if we adopt these rotational or angular variables. And instead of that, suppose you try to use these linear variables, then linear variables are different for different constituent particles. So the study would become very complicated. Just for our ease, just for our sake of convenience, we use these angular variables to describe any rotational motion. Got it? Last one small point about uniform circular motion. Don't you know uniform circular motion? What is that? A circular motion performed with constant speed is called uniform circular motion. See, both the speeds are constant. Linear speed is also constant, angular speed is also constant. Naturally, when angular speed is constant, angular acceleration will be 0. When omega is constant, alpha will be 0. Put alpha equal to 0 here. Put alpha equal to 0 here. When you put alpha equal to 0, AT will be 0. So, for uniform circular motion, there is no tangential acceleration. There is no A parallel component. Got it? And then tell me, when it is 0, put it here. So A will be simply equal to under root of AR square, that is AR. A equals to AR because it is 0. A equals to AR. A equals to AR. What was the formula of AR? Formula of AR was omega square R. Come on, omega square R. Okay. So in case of uniform circular motion, it has only one component of acceleration, that is a perpendicular or radial or centripetal acceleration, whose job is to change only direction of velocity, not to change the magnitude of velocity. Okay, because here magnitude of velocity is constant. Got it? Thank you.